In this lecture, let us talk about a feedback FM demodulator, especially by using phase locked loop. PLL means phase locked loop. In the previous lecture, we talked about the open loop FM demodulators. Okay, now let us continue. So, this is a closed loop FM demodulator, which are also called feedback demodulators. Closed loop in the sense some portion of the output is fed back to the input. Okay, so you have input, you have FM demodulator, and a portion of this is through feedback circuit is given to the input. So therefore feedback FM demodulator, or you can also call closed loop FM demodulators. Okay, because what we are discussing in this connection is going to be important for from several points of view. So the initial motivation for this discussion is to show that the very important class of FM demodulators or angle demodulators. So this one is very important. This closed loop form of FM demodulators, very important. Okay, however, they also have other applications. Not only they are used in FM demodulators, but they are also used in some other applications. For example, applications to which we referred to earlier when we were discussing synchronous amplitude demodulation. Okay, so we talked about the need for a local carrier which is synchronized with the carrier, particularly when we wanted to demodulate DSBSC. So whenever you have some synchronous demodulation, there we need this kind of closed loop FM demodulators. Okay, now the question is, how do you achieve that synchronization? That is again achieved through the same feedback devices which we are going to use for FM demodulation. So the closed loop FM demodulators are not only used in frequency demodulation, but it is also used to devise the synchronous demodulation for AM signals. Synchronous demodulation for DSB SC signals. There also we use this kind of closed loop FM demodulators. So although our initial motivation is to show how this is so called feedback demodulators, okay, like so called feedback demodulators which can be used to carry out demodulation of FM signals, we will also discuss some other applications of this separately as we go along. Okay, so the point is this FM demodulators, feedback FM demodulators, not only used to demodulate the FM signal, but also it is used in some other applications. Okay, basically the motivation for using this feedback demodulators over the normal discriminators that we have discussed in the last lecture is that they yield better performance in the presence of noise. Okay, in the last lecture we discussed FM discriminators, but compared to that, this feedback FM demodulators provide better performance. Noise. So it is improper to discuss it fully here, okay, because we have not yet considered the effect of noise on FM and AM signal for that matter. But when we do that, let me re-emphasize that discussion a little bit. That will give you a preview of the discussion. When you do that, you will find a very important characteristics. So the important characteristics that we will study later is, while the FM signal in general, FM in general is better in the presence of noise. Therefore, the therefore this closed loop FM demodulators gives superior performance in the presence of noise. That is why it is the preferred modulation to use in music broadcasting It also has certain disadvantages, okay, that also we'll discuss a little later. Maybe the disadvantage is bandwidth, right? The other disadvantage, of course, it has it uses much larger bandwidth, right? So the bandwidth of FM signal is much higher than the bandwidth of your AM signal. Okay, so the other disadvantage is it displays a phenomenon which is called threshold effect. One is higher bandwidth and the other one is threshold effect. So this threshold effect occurs only in FM, not in AM, only in angle modulation. So the threshold effect refers to the fact that the output is very nice if the input is good. That means if the input SNR is reasonably large, then output will be very nice. Okay, so there is a noise present, but not to an extent that something bad happens, and this is the problem. In FM, if the input SNR goes beyond a certain point, becomes very bad. Let's say then the output of the FM demodulator will goes very bad. I mean simply fails to resemble the input at all. Okay, so in this case FM demodulator simply breaks down. So there is a certain threshold SNR which you must maintain at the input of an FM receiver. If your signal is not strong enough, then what will happen? Your output will be of very bad qualities rather than a good quality. So there is a non-linear relationship between the input SNR and output SNR. But if you consider other modulation schemes, that is not like that. So this is the threshold effect which an FM receiver exhibits, but this threshold point we will discuss a little later. Okay, in detail we will discuss. Okay, so therefore your FM system is very nice up to a certain point, but it is very bad beyond that point. So it is a very good or very bad, nothing in between. So therefore your FM system is very good in some portion and it becomes very bad in some other situation. So nothing in between, average or good like that. Okay, that's what so why that happens we will see little later. And one of the advantages of going for feedback demodulators is that it can extend the threshold effect. So it can lower the threshold for us. So that is one of the reasons. So it is widely used. Okay, to extend the threshold effect, we are using this feedback demodulators. Therefore, the feedback demodulators are widely used. And the second advantage of this feedback demodulators is that they can be easily realized in integrated circuits form. Okay, first one is widely used. The reason is it increases the threshold point. That is the reason it is widely used. And second one is realized in an integrated circuits. ICs. The reason for that is typically in this kind of feedback demodulators, we don't use any inductors. If you recall from your frequency discriminator, where we used transformers, inductors, capacitor, and so on and so forth. Okay, in your balanced discriminator. Okay, so that is based on tuned circuits, stagger tuned circuits. Okay, it has two slope circuits. Okay, that we have talked about. They will be typically realized by using a linear portion of the resonant circuit. It has parallel LC circuit. Whereas there will be no inductors and capacitors in this realization. So that is the advantage of this feedback demodulators. So there are two basic kinds of feedback demodulators. and we will discuss first the most important of this. The most important of these two is called the phase locked loop. Okay, in short it is called PLL. So we are going to discuss the use of PLL for FM demodulation. But mind you, PLL is a very important component, and it has many applications. Okay, so the PLL is not only used in FM demodulation circuit, it is used in some other applications also. Okay, so the PLL has 4 basic components. Okay, so we will discuss as to why we call it by this name, okay, a little later. Okay, why is it called phase locked loop? Because that we will discuss, nothing to worry. So why this name has come? Okay, so we will first describe what it is. It as I said, it has 4 basic components, and there is a feedback involved amongst these components. So the 4 components are phase detector, and voltage controlled oscillator, then loop filter, and then 4th one is loop amplifier. So these are the 4 components it has. Okay, now let us take the phase detector and try to understand its working principle. So there is a phase detector. Let me put a block diagram like this. You have the input signal and there is another input signal. So it has 2 input and 1 output. Let us say input 1. Okay, so there are 2 sinusoidal inputs. Input 1 is a sinusoidal input, and input 2 also is sinusoidal input. But the beauty is, if this is cos omega c t something, this becomes sin omega t something. Okay, both will not be cos, or both will not be sin. That we will address this one, why one is cos and another one is sin. If both are same, then the phase detector will not do the purpose. Therefore, the output of the phase detector would be proportional to the instantaneous phase difference between these 2 inputs. Let us say this one is, let us say phi 1 of t, and this one is theta 1 of t, or theta of t, phi of t. The output will be phi of t minus theta of t. Output will be, okay. So the output of your phase detector would be proportional to the instantaneous phase difference between these 2 inputs. That is why we call it a phase detector. So you have a phase detector. The output of the phase detector is given to a loop filter. And then loop amplifier, and then this is my final output. Let me denote this as E suffix V of t, and then you put the voltage controlled oscillator in the feedback path, put it like this, and then this is my received FM signal X suffix R of t. Okay, like that. So therefore the phase detector is followed by a filter which is called loop filter, and we also have some amplification in the loop. So that is why we put this loop amplifier. Sometimes this loop amplifier is clubbed together with the filter and say filter itself. Okay, sometimes they will these two guys are clubbed together and simply they will call it filter itself. Okay, and then you close the loop through the voltage controlled oscillator. Okay, in the feedback path we have a voltage controlled oscillator. Okay, now what is voltage controlled oscillator? Okay, that we have discussed in the context of FM signal generation direct method, right? So a VCO is present in the feedback path of this circuit. If you feed an FM signal at the input, this is my input, at the input, then the input to the voltage controlled oscillator is taken from the output. Let's call this output is E suffix V of t, and this E V of t is the input to your voltage controlled oscillator. Okay, we will see that under certain conditions your output E suffix V of t will be proportional to the message signal M of t, proportional to the message signal M of t. Anyway, we will discuss that. How does it will be proportional to the message signal. This condition is true, or the output is proportional to the message signal M of t when the input happens to be an FM signal. We will see. Now let us see how it works. So now let us look at the operation of the circuit. Now at the input you have an FM signal. Let us the input is denoted by x suffix r of t, and this x suffix r of t I can write x suffix r of t is equal to AC times cos of omega ct plus phi of t. Okay, it contains the FM modulation. Okay, this is the FM modulated signal. In terms of the effect that phi of t will depend on M of t. What is the relation between phi of t? What is the relationship between phi of t and M of t? This is equal to 2 pi times k suffix f integral of minus infinity to t M of tau times d tau. Therefore, phi of t is directly related with the M of t. Okay, if you differentiate this equation, d phi of t by dt is equal to 2 pi kf times M of t. Remember this one. Okay, so your VCO is here, voltage controlled oscillator in this loop, and this will produce an other signal, okay, of similar kind. This type of signal it produces. We don't know what it will be exactly. Okay, so let's say this voltage controlled oscillator signal is let me call E naught of t. We don't know what it is. Okay, so let us say this E naught of t. We are assuming that, okay, we assume that E naught of t is equal to A suffix V times sine of omega ct plus some phase angle theta of t. So initially we are assuming that the output of voltage controlled oscillator is in this form, AV times sine omega ct plus theta of t. Okay, now my phase detector, let me write down the signal here, AC times sine of omega ct plus theta of t in this point, and here it has I'm sorry, this is AV, right? I'm writing wrongly. AV, and this one is AC times cosine of omega ct plus phi of t. Now we said your phase detector will be sensitive to the instantaneous phase difference between the two inputs. So it will be sensitive to phi of t minus theta of t. Therefore, in this point you will be having phi of t minus theta of t. Okay, and the feedback loop, as any feedback loop will try to do, what it will try to do is it will try to derive this error to 0. Therefore, in this feedback loop we will make it to approximately equal to 0. So the whole thing is designed in such a manner that it will try to drive this error to 0. Okay, so this is a difference. This difference is towards the 0. Okay, it will drive to 0. So suppose if that happens, okay, we have to discuss whether that happens or not. Let us assume, suppose if that happens, basically what we are saying is this theta of t will try to follow phi of t. That's what we are saying. If the difference is equal to 0, what does it mean? Phi of t is equal to theta of t. That means what? Your theta of t will try to follow phi of t. Theta of t will try to follow phi of t. And if theta of t follows phi of t, what is the relationship between the message and the phase? Just now we derived. Your phi of t is this one, and d phi of t by is 2 pi k f m of t. Therefore, your theta of t is also 2 pi k f times integral of m of tau d tau. Okay, messages are the derivative of the phase. What is the message? D phi by dt. This d phi by dt is the same as d theta of t by dt, right, is equal to 2 pi times kf times m of t. So that means d theta by dt follows the message. That means what? The input to the output is my message. The output of my voltage controlled oscillator is omega ct plus theta of t, and this theta of t follows the message. That means the input is message. Okay, that means the input to the VCO, because after all the instantaneous frequency of the voltage controlled oscillator, that will depend on the input voltage. Now my theta follows the m of t. That means what? This theta of t is controlled by the input signal. So my theta of t is proportional to m of t. That means the input is m of t. Okay, so that's the basic idea. So what we are saying is we will try to make this error, drive this error to 0. If you are driving this error, if you are trying to drive this error to 0, that means what? Your theta of t follows the phi of t. Okay, now what is phi of t? We have given this one, right? This is my phi of t. Now if theta of t follows phi of t, then theta of t also will be the same thing. Now your output of your voltage controlled oscillator depends on the input voltage. What is the output of your voltage controlled oscillator? AV times sine omega ct plus theta of t. Therefore the output theta of t depends on the input. What is theta of t? It's a message signal. Therefore the theta of t depends on the input voltage signal, which is nothing but m of t. So we can ensure that this loop works in such a manner that the instantaneous phase of the voltage controlled oscillator output tries to follow the instantaneous phase in the input signal. Then the input to the voltage controlled oscillator signal will try to follow the message signal, and therefore you would have got at this point, in this point your message signal. Okay, that you are looking for. Okay, so this is the basic block diagram of your phase locked loop. As I said, it has 4 blocks: phase detector, loop filter, loop amplifier and voltage controlled oscillator. Okay, now we assumed that the input is the angle modulated signal, let's say frequency modulated signal, which is given to the input of your PLL. Okay, and this input has certain amplitude and the carrier frequency and phase phi of t. Let me explain this one more time, because it is little okay, fine. Now this is my input, as I said. Input is denoted by x suffix r of t. What is x suffix r of t? It has certain amplitude. Let me denote by a suffix c, okay, with the carrier frequency omega ct and some arbitrary phase modulation phi of t, okay, which will depend on what is the nature of this signal. Okay, so EV of t, this is my output, right? Now, because after all the voltage controlled oscillator is governed by its input, what is the input now? EV of t. So depending on the variation of input, it will have some modulation. Okay, so it will have some modulation here. Therefore, my output of voltage controlled oscillator, let me denote by E naught of t. So E naught of t is equal to a suffix v times sine of omega ct plus theta of t. Okay, and this theta of t is controlled by your EV of t. So you might notice that I have chosen the input signal as a cos function, right, cosine function, and the received output signal to be a sine function. Okay, so this I have chosen deliberately. Okay, so this is deliberate, and you will soon see the reason of why I have chosen like that. Okay, now let's proceed further. First of all, the first question one would like to ask is, how do we realize the phase detector? Okay, that is realization of your phase detector. Okay, let's discuss this issue first a little bit, and then we will look at the operation in more detail. A very simple realization of the phase detector is as follows. In fact, there are many ways of realizing the phase detector, but we will take the simplest one. So one of the simplest ways is to simply have a multiplier followed by a low pass filter. Okay, so this is your input x suffix r of t. For the multiplier I need two inputs, right? So this is my e suffix v of t phase detector. Hold on 1 minute. Let's say e suffix o of t, output of your voltage controlled oscillator. Okay, E naught of t, this is my output, and these two blocks together is called a phase detector. Now let us see how it detects the phase. Okay, so this input is your x r of t, and here the input is e suffix o of t, As you can see, let me call this point is capital A. At point A, it will contain the some frequency component as well as difference frequency component. Why? Your xr of t, x suffix r of t is equal to AC times cos of omega ct plus phi of t, and your A naught of t is equal to A suffix b sine of omega ct plus theta of t. Use your trigonometric identities. Okay, cos A sin B, then this is equal to product of these two guys is equal to AC times AV times multiplied by cos A cos B, sorry, cos A sin B or sin A cos B is equal to sin of A minus B. Okay, omega ct minus plus phi of t minus omega ct minus theta of t. Okay, so this is one term plus sin of A plus B, it becomes 2 omega ct plus phi of t plus theta of t. Okay, now I have two components. Okay, one is sin of this component, and before that these two components will get cancelled. So this is equal to AC AV I forgot to put the term 2 here, by 2 times sin of phi of t minus theta of t plus sin of 2 omega ct plus phi of t plus theta of t. Now in this, what will happen? You are passing this through the low pass filter. So at point A, I have two components. Okay, the sum frequency component as well as the difference frequency component. This one is sum frequency component, sorry, difference frequency component, and this one is sum frequency component. Because we are adding two frequencies, and this one is the difference frequency component. Now if you pass these two guys to the low pass filter, then this 2 omega c is a very high frequency though, so this will be rejected. So the sum frequency component will be rejected, and the difference frequency component will be the low pass component. Okay, since omega ct is same in both of them, and the difference term will contain only the difference between two arguments, theta of t, phi of t and theta of t, and the sum will be at a frequency of centered at 2 omega c. So which will be removed by the low pass filter. So basically if you look at the output of the low pass filter, in this point let me call B, output of the low pass filter, then it contains only the difference frequency component. So therefore I am realizing the phase detector as a set of these two blocks, multiplier, this one is multiplier and low pass filter. Therefore this difference output ED of t is equal to 1 by 2 AC times AV times sine of phi of t minus theta of t. Okay, so this combination of a multiplier followed by a low pass filter will produce an output which is this one, 1 by 2 AC AV sine of phi of t minus theta of t. And as you can see, this output ED of t is a function of the phase error. So this phi of t minus theta of t is called what? Phase error. Okay, or you can call instantaneous phase error. Okay, so if you consider phi of t as an instantaneous input phase, this one is instantaneous input phase, then theta of t as the instantaneous output phase coming from where? VCO. If you look at the diagram, then you'll come to know. So this is coming from the voltage controlled oscillator. So your theta of t is the instantaneous phase coming from the voltage controlled oscillator. So therefore this is my difference in the instantaneous phase error. Now if you look at this equation, of course this is not a linear equation. Okay, it is not linear dependence. Okay, it is a non-linear dependence because of the sinusoid function here, because of the sinusoid. But nevertheless, it is it is a dependence, right? Of course, when phi of t minus theta of t is small, then this non-linear dependence will also become linear dependence. Okay, so like if theta is very small, theta is approximately 0, then sin theta is approximately equal to theta, right? Please remember this rule. Therefore sin of phi of t minus theta of t becomes phi of t minus theta of t if this guy is very small, very small. I mean, if the error is very small, then your non-linear equation becomes a linear equation. Okay, the non-linear dependence will become a linear dependence, because you can approximate sin phi of t minus theta of t is equal to phi of t minus theta of t when the argument is small. Okay, so AC times AV times K suffix D is a phase detector constant. This is, so I forgot to put that phase detector constant. You put KD here, phase detector constant. A 1/2 so let me write down the equation again. This E d of t is equal to AC times AV. This AC is from the carrier and this is from your VCO, and this A suffix D is from phase detector. Okay, times sin of phi of t minus theta of t, and of course 1/2. Okay, and this KD is associated with the multiplier constant. So there are other ways of realizing the phase detector, but broadly this is the general principle. Okay, this one multiplier followed by a low pass filter is the general principle. Okay, we can of course build from other devices also. So this is how the phase detector of the PLL will be characterized, okay, in our model, because typically we will realize it using this combination, multiplier and the low pass filter. Okay, now let us look at how the voltage controlled oscillator can be characterized, because once I know the characterization of each block in this one, how the loop filter is characterized or realized, how your loop amplifier is characterized or realized, and how your voltage control is realized, and how your phase detector is realized, then I can analyze this feedback FM demodulator very easily. Okay, so I can proceed with the analysis of these loops. So that's what I am going to do now. So phase detector is okay now. Okay, so the phase detector is modeled by a multiplier followed by a phase detector, and the output of the phase detector is this one, AC AB AD by 2 times sine of Vt minus theta of t, and this AC is your carrier voltage, and AV is coming from your voltage controlled oscillator, and AD is the, which I wrote here, associated with the multiplier. Okay, now let's move on to voltage controlled oscillator. How do we model the voltage controlled oscillator? See, the VCO can be modeled in the same way that we modeled an FM signal. Okay, when we discussed your frequency modulator, where we had two types of modulators, one is a direct type and another one is indirect method. In the direct method we used voltage controlled oscillator. Okay, after all, your voltage controlled oscillator is performing the FM modulation operation. It will produce an output whose frequency deviation depends on the input voltage. So that is the characterization of the voltage controlled oscillator. So it is the same characterization that we are going to use here also. So what is an instantaneous frequency duration of the signal that I have just depicted? The output of your voltage controlled oscillator is AV times sine of omega c t plus theta of t. Okay, you are saying that the VCO is producing an output which is A suffix V times sine of omega c t plus theta t. Now what is the instantaneous frequency deviation? See, the instantaneous phase deviation is theta of t. Phase deviation. Now the next question is instantaneous frequency deviation. And this one is given by derivative of your phase d theta by dt. And this instantaneous frequency deviation must be proportional to the input signal. Why? That is the principle of your voltage controlled oscillator. This is my m of t. My output frequency must be proportional to what? My m of t. What is f here? F is nothing but this one, instantaneous frequency deviation. Therefore, d of theta of t by dt must be proportional to m of t. Okay. Now, if you follow that notation that I have used in the diagram in the phase locked loop, input signal to the voltage controlled oscillator is what? Not m of t, we said EV of t. Recall your figure. Okay, this is my E suffix V of t. Okay, therefore, in the voltage controlled oscillator, the input is EV of t. Maybe I will draw in the same style. VCO, the input is E suffix V of t, and this is my output. Okay, therefore, d theta of t by dt is equal to some constant. Okay, let me call it that constant as kV. Okay, some constant times my input signal. My input signal is E suffix V of t. Okay, now if you want to model the phase itself, then your theta of t is equal to kV times integral of minus infinity to t E suffix V of t or E suffix V of tau times d tau. So these are the two equations. Let me call equation A and equation B. So these are the two equations which will model the voltage controlled oscillator. Okay, and I'm sorry, error mark I put wrongly. It is coming out. So this one is AV times sine of omega ct plus theta of t. That's it. So the instantaneous phase of the voltage controlled oscillator is governed by, let's say, this equation B or equation A. Okay, this is my instantaneous phase. This is instantaneous frequency, and this one is instantaneous phase. Therefore, the instantaneous phase of my voltage controlled oscillator is governed by this equation B. And this one is the standard FM equation. Okay, so really nothing special about it. And this kV here is VCO constant, voltage controlled oscillator constant, proportionality constant. So therefore you can substitute this guy into your equation here. Of course, you can work out, okay, what will be the dimensions of all these constants that we have discussed, okay, AV, AC, all those things, kV, kd, like that. So we now have the characterization of every component that we need. So this is the characterization of your voltage controlled oscillator. So we finished just now the characterization of phase detector, okay, and of course we already know the characterization of the filter, how to characterize an amplifier, and also we know how to characterize the amplifier. So the two components that we have introduced were the phase detector and the voltage controlled oscillator. Okay, we have enough knowledge about your filter, loop filter and loop amplifier, no problem. So the new components are phase detector and voltage controlled oscillator. Like this. This is my EV of t, E naught of t, XR of t, and so on and so forth. So these two components are new components for me, phase detector and voltage controlled oscillator. So having got the characterization for each of them, let us develop a mathematical model which will serve as a framework for our discussion or understanding of the working of the PLL. Okay, so our next job is, let us try to develop the mathematical model. So in this mathematical model, it would be nice if I can get rid of this carrier frequency omega c, okay, because your XR of t is equal to AC times cos of omega ct plus phi of t, and here AV times sin of omega ct plus theta of t, and here also omega ct and here also omega ct. So no need of consider that. So omega c has no direct role to play in this discussion because omega c is present in the input as well as in the output of your voltage controlled oscillator. In fact, for all practical purposes, okay, what is that I would like to do? I would like to see and understand how the phase locked loop produces an output whose instantaneous phase theta of t is close to the input phase, which is phi of t. So for all practical purposes, I need to consider this phi of t and theta of t. Least bother about the omega ct. Okay, I can consider phi of t as some kind of input to the system. Okay, so think of this as a system, this whole block diagram, these 4 blocks, and okay, the input to this whole block diagram is phi of t. Let us assume phi of t, and let us assume this is unknown phase. So we are trying to find out the unknown phase, and I want to produce an output in a closed loop manner such that my theta of t, okay, is very close to your unknown phase. So I am trying to estimate my theta of t which is close to the unknown phase theta of t. So if I want to do that, I can redraw this diagram in terms of an equivalent circuit. Okay, so I put a summer here and the input is phi of t. For the time being, I am for not considering this carrier terms and all, and here the term is VCO is replaced by integral of kV times what, your theta of t, like this. Okay, so the above circuit, this phase detector, loop filter, loop amplifier and VCO is replaced by like this. Okay, so I am now talking about a mathematical model for the phase locked loop, okay, which will help us to do the analysis, and it turns out to be a non-linear model. Now we will see why this is a non-linear model very soon. And this one is, the output is given to, this is minus and this one is plus, and sign of this like that. Now at the input we have unknown phase, See, I am not considering the carrier component, I am simply assuming that the input is phi of t and the output of my voltage controlled oscillator is theta of t. So I am putting minus here and plus here. Therefore in this point phi of t minus theta of t. Now I am taking sine of this guy. So here I will get a sine of phi of t minus theta of t like this. And theta of t is the incoming phase, and I am comparing this phi of t with the phase of voltage controlled output oscillator. That is, the phase detector compares the phase phi of t and theta of t. Okay, so what does it do? It produces an output which is of difference of these two. So that difference is written over there. And then the phase detector output is proportional to the sine of this difference, phi of t minus theta of t. Okay, and there is a sine function here, trigonometric function, and this sine function is a non-linear function, highly non-linear function. Okay, this output is called E suffix d of t. So E suffix d of t is equal to sine of phi of t minus theta of t. Okay, now in this you have kV is there, and the input side you have AC, right, and then AV is there, your voltage controlled oscillator output. So this all three constants are there. Okay, so the constants are equal to 1 by 2 AC, AV and AD. One is multiplier constant and one is VCO constant and another one is the carrier constant. So these three terms are there. So those three terms are missing. Therefore I can rearrange the above diagram, this diagram as, you put a summer, you put plus here, minus, this is phi of t, theta of t, integral of dt, and this one is sine of the difference. Then you put the 1 by 2 AC, AV and AD. So this is my ED of t. Therefore my ED of t is equal to 1 by 2 AC, AV, AD sine of phi of t minus theta of t. Okay, so this circuit becomes like this. Okay, so there is an amplifier. So this is what? Amplifier. So I can think in terms of an amplifier, and the amplification factor is 1 by 2 AC times AV times AD. Okay, and that is a gain. And where does it come from? This AC is coming from the carrier and AV is coming from your, I already wrote, right? You can see, look at here. Where did I write? Yeah, this AV is coming from your phase detector, right? Yeah, this AV is coming from your voltage controlled oscillator, and the multiplier constant is KD. So again I made a small mistake, it is not AD, it is KD. This is K suffix D, and this one is not AD, it is K suffix D. That's it. So so far I have produced a sine of phi of t minus theta of t. If I want to produce this ED of t, the way I have depicted earlier, I must multiply sine of phi of t minus theta of t with this constant 1 by 2 ACAV times KD. So I am multiplying the gain of this much in the block diagram. So this is your ED of t, okay, at the output of your phase detector. Now let us put everything in the block diagram now. So the input is phi of t plus and minus integral of dt now this one is sine of that function, and then for the moment let me break them. Sine of that function, then you have multiplication factor AC times AV times KD, and this one is given to loop filter and loop amplifier. And now what should I put here? Okay, we have the loop filter. The output of the loop filter is given to the amplifier. Okay, let us say the amplifier has some gain mu. Its gain is mu. And now what should I put in between this point and this point? What should I put? And this point is theta of t. Okay, now what should I put to close the loop? Okay, how will the VCO be represented here? The VCO is not being represented as producing an output which is sin omega ct plus theta of t. It is now being modeled as producing an output which is equal to theta of t. So this is purely a mathematical model for what the VCO is doing. So how is theta of t related to these 2 points? And this one is EV of t. So the amplifier output is EV of t. Now how this amplifier output and the input to this point, these two are related through the integral relation dt. Okay, so to close the loop, all I have to put is an integrator here. This already we discussed, okay, just now we discussed the integrator. See, it is over there, integrator. So this loop amplifier has a gain mu, loop filter, and this is the 1 by 2 ACAV times KD, this constant. And I forgot to put the arrow mark, you put the arrow mark. So like this. Okay, so I think with this figure, this should be, okay, this figure is fairly enough to understand the concept. Okay, so I think this should be fairly clear from the development that we carried out. So this is the mathematical model. Okay. From this mathematical model, you can study to understand how this works and how precisely what it will be able to do and what it will not be able to do also. Now let us take this circuit, this block diagram, and do the analysis. Now we are going to do the analysis in two phases. So in phase 1, we will assume that somehow the loop comes in the lock condition. Lock means what? Your theta of t is, your phi of t is equal to lock condition, phase 1. So we assume that somehow your loop is locked. That means your phi of t minus theta of t is approximately equal to 0. What does that mean? Phi of t is equal to theta of t. Sorry, theta of t is equal to phi of t. Your theta of t follows the phi of t. Okay, so this assumption we are making to simplify our study and somehow try to understand. Okay, let us assume that the loop is somehow locked. Okay, and then try to understand when the loop is locked, what is the nature of your EV of t, nature of E of t. In phase 2 of our discussion, obviously should try to tell us how your lock actually happens. Okay, so in phase 1 we assume that lock has arrived, but in phase 2 we will study how that lock actually happens. Okay, so we will go through the discussion in two phases rather than trying to understand everything in one go. So in the first instance, assume that PLL is operating in a locked condition. So the first one is PLL is, maybe I'll write down clearly. Assume first that the PLL is operating in a locked condition. We will see what it means. Okay, so you can simply say that the PLL is locked. So what is the meaning of this PLL is locked? This being in a locked condition, what we are trying to say by this is that theta of t is a very good estimate of phi of t. Okay, that means theta of t minus phi of t is small, very, very small value. So that's what the lock condition means for us. It may not be exactly the same, but it is a good estimate of incoming phase phi of t. So this will imply in turn that the error between these two, if at all there is a difference, would be small. So that is the meaning of the lock condition. Okay, so therefore theta minus phi of t could be small in the lock condition. And if that is so, we can approximate your sine of phi of t minus theta of t is approximately equal to, either you can change this okay, approximately equal to phi of t minus theta of t. Okay, so assuming that this is small. Now when the loop is not in locked condition, we cannot say that. Okay, but this may be considerably large in this case. This may be considerably large in that case. So when the loop is not in lock condition, this approximation cannot be used. When the loop is operating in the lock condition, it is convenient to use this approximation, because what it will do is it will convert this non-linear equation into a linear equation. I mean non-linear model, right? This is a non-linear model. So if the loop is in locked condition, then what will happen? This non-linear model becomes a linear model. Why is it a non-linear model? Because the presence of the sine function here. Look at here, there is a sine function. Because of the presence of this sine function, otherwise everything else is linear. Okay, so your integration is a linear operation, and the filter is linear, amplifier is linear, this gain also linear. Okay, so this adder also linear, everything is linear except this guy. Okay, except for this block. Here the input is something and the output is sine of that. The input is something, the output of this one is sine of that. So sine of phi of t minus theta of t. Okay, so however, if I use this approximation, this also becomes linear now. Therefore, the non-linear block diagram becomes a linear block diagram. Okay, and that gives us what is called a linearized model of the phase locked loop. So if this condition holds, then you'll get a linearized PLL. And once you have this, of course, I think you haven't yet gone through the course on control system. I don't know. It doesn't matter. Okay, we will not need that background, in fact, from your control systems. But whatever we need, we will develop it here. Okay, nothing to worry. So we will use it here. So your PLL becomes then a linear feedback control system, right? So PLL becomes a linear feedback control system. When you are working with a linear feedback control system, you will find that it is very convenient to work not only in the time domain that we have discussed. In fact, it is more convenient to work in the transformed domain. So here we are going to use the Laplace transform domain. Okay, take the Laplace transform domain rather than the Fourier domain. So very briefly, we will also work with the Laplace transform domain, although most of the time we will not. So if I work with the Laplace transform domain, this linear model becomes okay, something like this. Okay, with the Laplace transform. So the input is phi of t, you put a summer, and this one is theta of t. Okay, so the original, let me rewrite the circuit. That sine function, and this sine function we are putting a straight line here. The sine is removed because of the locked condition, and then 1 by 2 AC, AD and KD, right? Sorry, AV times KD. Okay, now this phi of t becomes capital phi of S if you take Laplace transform, and this theta of t becomes put a capital theta of S. Okay, and in the feedback path, that integrator becomes 1 by S, and this amplifier has some constant mu like this. So this is your block diagram. In S domain. Okay, so I can only deal with the linear systems using Fourier transforms and Laplace transforms. So that is a convenient thing to do. So this sine is removed. So the sinusoidal things goes because of this approximation. Because of this approximation, the sinusoidal block goes. That means directly I can connect to this guy. Straight away I can connect like that. So you only have the next stage, which is the gain 1 by 2 times AC times AV times KD. Okay, and followed by the loop filter and followed by the amplifier. And let me call it again mu for your amplification and followed by the integrator. Okay, since we assumed that the loop is in a locked condition, which means that phi of t is approximately equal to theta of t. This is, the difference is very small. So basically what we are saying is phi of t is approximately equal to theta of t. So this would in turn imply that d phi of t by dt is equal to d theta of t by dt approximately, right? So we said d phi by dt is proportional to what? Message signal, right? If the input is an FM signal, recall from your previous theory. See, AC times cos of omega ct plus phi of t. This is my FM signal. What is your phi of t? Phi of t is 2 pi kf integral of m of tau d tau. What is your d phi of t by dt? Is equal to 2 pi kf m of t. That means d phi of t by dt is proportional to m of t. If d phi by dt is proportional to m of t, then this guy also proportional to what? M of t. And since these two are approximately equal, what does it mean? That EV of t, where is EV of t? This point. Okay, your EV of t is my demodulated output. Because in this point I have d theta of t by dt, and this is proportional to what? Your input. What is the input? Just now we got input is m of t. It's a very important point to understand here. If the loop is locked, then your phi of t is close to theta of t. That means d theta of by dt is approximately equal to, d phi by dt is approximately equal to d theta by dt, but d phi by dt is proportional to m of t. So this is proportional to m of t. Hence your d theta by dt is proportional to m of t. But is d theta by dt is output of my integrator. Okay, and now what is the input? Input is my message signal. Okay, this is proportional to m of t. So therefore the input will be m of t. But what is m of t? This is your message signal that is coming from after demodulation. Therefore this point indicates demodulated output. So this is the point that at the moment you need to understand. Therefore in this case E suffix v of t, this is E suffix v of t. E suffix v of t represents demodulated output. We are not talking about how this locking occurred. Okay, we are assuming that locking has occurred, and then we are talking about what is the demodulated output. Okay, so therefore I can summarize the discussion in the following way. When the loop is locked, then this is the condition, and then d phi by dt is d theta by dt, and therefore the input to the VCO is the demodulated output that you are looking for. Okay, I mean we have to still of course understand the mathematical analysis of this loop, which we'll do as we go along. But right now, even without going through any mathematics, we can conclude that in the lock condition, the output EV of t is proportional to the message signal m of t that you are looking for in an FM demodulator, and therefore the phase locked loop in a locked condition works like an FM demodulator. Okay, we have to still do the mathematics, but without mathematics, this is where it is. And then the next step that we have to take up is how does the locking actually occur. Okay, that is my second phase. So you have to understand how does a PLL, okay, how does a PLL walk into the locked condition, okay, walk into a lock condition. So we like to show that the phase error that we have at any instant, whatever the phase error we have, will tend to drive the PLL into a locked condition. So that is the second stage of our discussion. Phase 2. To show that phase error tend to drive PLL into a locked condition. Okay, so what is my diagram? One by S. Okay, recall from your Laplace transform. Okay, basically this is my integrator. Integrator, if you take Laplace transform, it will be 1 by S. Differentiator, if you take a Laplace transform, then it becomes S times something. Okay, so in the integrator it becomes 1 by S. That is why this block contains 1 by S. So here the sine function has gone 1 by 2 AVAC, then KD, then loop filter. So this is what we had in the locked condition. Okay, so we like to show that whatever instantaneous phase error theta of t, phi of t minus theta of t the loop has, or whatever error you have here in this point, okay, at any time I shouldn't use this diagram. Okay, this diagram I cannot use it. Okay, because why? This diagram is approximates only when the error is very, very small. If the error is not small, then this diagram is wrong. Whenever the error is very, very small, then I can use that approximation, that is sine of phi of t minus theta of t is approximately equal to phi of t minus theta of t. If phi of t minus theta of t is not equal to a small value, then I cannot use this diagram. Okay, so I need to modify this diagram. How can I modify? Our old friend, this is my phi of t, theta of t, you put kv times integral dt, and this one is sine of that function, then 1 by 2 AC AV KD, then loop filter. I need to consider everybody. Loop filter, gain with mu amplifier, and this point is EV of t, and this point is A naught of t. Okay, so the loop will work in such a manner that this point, at this point, the error will tend to become small. Okay, therefore the loop will tend to be in a lock condition. Remember, here I cannot use a linear model in this. This is no more a linear model, it is a non-linear model because the error is not small. Okay, because initially the phase error may not be small, so I must at this stage work with a non-linear model. So in the previous diagram we assumed that somehow the loop entered into the locked condition. So that is why our block diagram was a linear block diagram, a linear model, but now it is a non-linear model because of this sine function. Okay, once a lock has been achieved, we can work with a linear model, no problem. You can remove the sine guy. Okay, so let us try to understand this thing. So to carry out this discussion, I will again simplify the discussion somewhat. Okay, so what I am going to do this, in this I will assume that the loop filter is absent. Let us remove this loop filter. Okay, if you put everything together, then the analysis becomes very difficult. Okay, so remember there is already a filter which is inbuilt into the phase detector. Your phase detector also has one filter, that is a low pass filter. Okay, so we are assuming still there, but the additional loop filter, this for the time being we are going to remove it. When the additional loop filter is not there, we will call it a first order loop. Okay, as to why we call it first order is something will become obvious later. Right now we will assume that this loop filter is absent. Okay, my next assumption is, let me state this assumption. We will assume that loop filter is absent. So first order loop. Therefore this diagram becomes phi of t, theta of t, then sine of this guy, then 1 by 2 AC AV KD, then there is no loop filter. Okay, and then integral of KV times dt, then gain with mu like this, like that. Okay, so in this case we will find that the phase locked loop works even when there is no loop filter, and then we will try to understand in what manner a loop might help. At the moment we will assume that the loop filter is not present at all, so we remove that. So this condition is only for simplification of our analysis, only for the sake of analysis. Now this point is my EV of t. What is my EV of t? EV of t is equal to 1 by 2 AC AV KD times sine of phi of t minus theta of t. Okay, now let me denote this complete thing by k suffix t. So k suffix t times sine of phi of t minus theta of t. Okay, and what is phi of t? Phi of t is input phase, and this is the output phase, because output phase is coming from the because this is called output phase. The reason is because it is coming from the output. Now what is your theta of t? Theta of t is equal to k suffix t times integral of sine of phi of alpha minus theta of alpha times d alpha into limit is, let's say there is no limit, and of course this t does not denote time. Okay, and this t denotes total gain. The total, this is called k suffix t, and here this t indicates total gain, total. Don't confuse with the time. Okay, this AC, AV, KD are amplitude terms, but effectively they are coming with as a product. So this is called the loop gain, total loop gain. So that is why I am putting k suffix t. Okay, so don't confuse this t with time. So here t stands for total. So I could have properly put some other notation, but anyway let's keep it small t. Now let me draw this modified diagram. Anyway, let us take the same diagram, this one, and this point is your ED of t. Now you are looking at this output. This is my output. Okay, my output is integral of this guy EV of t. So output is equal to integral of EV of t and dt. And what is EV of t? EV of t is nothing but ED of t multiplied by mu. Okay, except for including mu. So I am able to do this because I am ignoring the loop filter. Okay, so that's why I can write EV of t in terms of E suffix d of t. E suffix d of t is here. Therefore, EV of t is equal to mu times ED of t. In between the path you have the multiplication factor mu. Therefore, this EV of t and ED of t becomes the same thing. Okay, become the same except for the constant mu. So ED suffix t times mu is equal to EV of t. So that is why EV of t is EV of t is equal to, from the block diagram you can write 1 by 2 AC AV KD mu times sine of phi of t minus theta of t. So alternately I can write this equation as integral no, this is correct only. Okay, now let us write down the theta of t. This my output is what? Theta of t. Okay, so output is my, see, this is phi of t and this is my theta of t. Theta of t is nothing but my output. Therefore, output is equal to theta of t is equal to integral of EV of tau and d tau, or I can put EV of alpha and d alpha. Let me consistent with my notation, alpha and d alpha. So integral of 1 by 2 AC AV KD mu times sine of phi of alpha minus theta of alpha times d alpha. Okay, so this whole thing let me denote by k suffix t. So k suffix t integral of sine of phi of alpha minus theta of alpha times d alpha. Now this is my theta of t. What is d theta of t by dt? Which is kt times sine of phi of t minus theta of t. Okay, let me call this as equation number 1. Actually, this equation 1 governs the dynamics of the loop. Dynamics of the loop. At any time instant, phi of t is my input phase, and theta of t is my output phase. This one is input phase. So the output phase at any time instant as a function of the input phase, which is governed by this non-linear differential equation. Okay, what is this? This is my output. Look at here. This is my output phase. That output phase is governed by the non-linear differential equation. Okay, so this equation 1 is the non-linear differential equation which we have now arrived at, and it provides a means to study how your theta of t will evolve as a function of time. So if I know how to solve this equation 1, if I know how this equation 1 will behave, that will give me an understanding of how theta of t behaves as a function of time with respect to phi of t. How my theta of t will vary with respect to my phi of t with respect to time. So that is what I want to study. That's what I need to study. Unfortunately, because this is a non-linear equation, it is very difficult to study. Okay, so unfortunately it is very difficult to study. So we need to evolve special methods of trying to get an understanding of how this works. If it is a linear differential equation, then you can straight away find the solution, like finding its complementary function and particular integral, and then you can find out how the things are evolving and how your theta of t varies with respect to phi of t. But here it is a non-linear differential equation. Therefore, to do that discussion, further we will do the discussion when phi of t is a special kind of function rather than a general kind of function. Therefore, the general solution of this is very cumbersome, very difficult exercise. To simplify the discussion further, let us assume that phi of t has some special nature. What does it mean? Phi of t represents what? It represents the phase modulation at the input. Okay. So I am going to make that modulation very simple. That's all I am saying. So to study the effect and to study how the phase locked loop actually lock. So to do that, what I am going to say is, let the input to the FM modulator at the transmitter is input to the FM modulator at the transmitter is a very simple kind of signal. See, at the transmitter you have the input signal m of t and the output is x of t, and this you give it to the antenna, and after maybe some 10 kilometers you are receiving this signal, and this is my xr of t. Right. Now in the transmitter side I am going to assume this m of t, like instead of a general signal, see this m of t is a general signal, right? This m of t is going to be like your voice, music, speech, like that. But what I am saying is, instead of giving this general signal, I am going to give this simple kind of signal that I am considering here, which is proportional to unit step signal. M of t is proportional to your unit step signal. Okay, so therefore your m of t is, let's say, delta omega times u of t. Okay, so that is a simplification I am bringing about now to solve this non-linear differential equation. Straight away you cannot solve it, so you do some kind of simplification and try to understand. Therefore let the input to the FM modulation or modulator be proportional to a unit step function. Okay, so I am sorry, let me, therefore if you differentiate, sorry, this is correct, I am sorry, oh my god. Okay, now we said your d phi of t by dt is proportional to m of t. Now let us make the proportionality constant is 1, therefore your d phi of t by dt is equal to delta omega times u of t. So the instantaneous frequency, what is d phi by dt? Instantaneous frequency. So the instantaneous frequency is d phi by dt, and let's say it is a constant value, okay, delta omega multiplied by u of t. Okay, that means what? Your FM modulator was producing a times cos of omega ct without any modulation, because when t equals 0 it becomes u of t. At exactly t equals 0 it changes its modulation. For t less than 0 it produces a times cos omega ct. When t is greater than or equal to 0 it produces a times cos of omega ct plus delta omega. Okay, delta omega times u of t. That's what I am saying now. Okay, suddenly you provide a step change in the frequency. Okay, there is a change in the frequency. It produces omega ct up to in this point. At t equals 0 you apply this step function, this one. Therefore your frequency will be increased by delta omega times u of t. Okay, so that is equivalent to m of t being a step function. So you are producing a step change in the input signal. Okay, you take your m of t to be unit step function such that this change in amplitude of the input to the modulator produces a frequency deviation of delta f. Okay, the frequency deviation. So before applying the unit step, your carrier frequency was fc. The moment you apply the step change, then your carrier frequency or your instantaneous frequency becomes, it is fi. Fi equal to fc before t equals 0. Then your fi becomes, after applying the unit step function, your fi becomes fc plus this delta omega, or let me write delta f. Initially the carrier frequency was fc, now it becomes fc plus delta f. So this kind of simplification I am talking about will help us to okay, so this type of simplification will help us to simplify the non-linear analysis, non-linear differential equation. So that is the only purpose we are talking about this. Therefore, d phi of t by dt is equal to delta omega times u of t. Now, what is a phase error? We said phi of t minus theta of t. This is my phase error. Okay. Now let me denote this phase error by psi of t. Psi of t is equal to phi of t minus theta of t. So this is my definition. I put a triangle symbol here. Now d psi of t by dt is equal to d phi of t by dt minus d theta of t divided by dt. Why I am doing this in differentiation? Because I want to write in terms of instantaneous frequency. Therefore, my d theta of t by dt is equal to d phi of t by dt minus d times psi of t by dt. But d phi by dt is modeled by what? This equation. D phi by dt is delta omega times u of t. Okay. So therefore, you can substitute here. So I am writing the equation only for t greater than 0, right? Therefore, d phi by dt becomes, d theta by dt becomes, this is delta omega times u of t minus d psi by dt. This is my d theta of t by dt. For t is greater than 1, this u of t becomes 1. Therefore, d theta of t by dt is equal to delta omega minus d psi of t by dt, provided that t is greater than 1. Now what is this d theta by dt equal to? Do you remember? This is what? Recall from your figure, okay? So your theta of t is equal to k suffix t integral of sine of phi of alpha minus theta of alpha times d alpha. If you take d theta of t by dt, then it becomes k suffix t times sine of phi of t minus theta of t. So substitute back here. So therefore this equation becomes k suffix t times sine of phi of t minus theta of t is equal to delta omega minus d psi of t by dt. So this equation is valid only for t greater than 0. So what do I have now? Basically I have derived this equation. So I have a differential equation for the phase error. So if you rearrange this equation, then d psi of t divided by dt plus k suffix t sine of phi of t minus theta of t is equal to delta omega for t is greater than 0 or greater than or equal to 0, no problem. So for the special case when the FM signal is essentially a step change in a frequency at the input to the PLL, the governing equation for the phase error is this differential equation. And we like to understand under what conditions will this, let me call this is equation number 2, will this differential equation imply a movement towards psi of t becomes 0. What is our ultimate goal? Psi of t should move towards 0. So how does the psi of t becomes 0? Because what is my psi of t? Psi of t is my phase error, phi of t minus theta of t. So now we need to understand such that at what conditions will this differential equation imply a movement towards psi of t becoming 0. So how does the psi of t becomes 0? How does the psi of t become 0? Okay, whether or not it will become 0. So by studying this differential equation. Okay, so whether or not it will become 0, that will be answered by studying this differential equation. Now when you want to study non-linear differential equation, one physically appealing way is to represent the behavior of this equation pictorially by in a diagram called a phase plane plot. Okay, so we like to see how that happens. So we like to try to understand and study this through a device called phase plane plot. So when you come across a equation like this, some kind of non-linear equation, then straight away finding its solution is difficult. So in that case we will draw the behavior of this non-linear equation pictorially by in a diagram called a phase plane plot. Okay, so that we will discuss in the next lecture. So let me stop at this point. Thank you very much.